First lesson on Unit 6 is on e to the x, log x, a to the x, and its derivatives. Well, we have to kind of evaluate and analyze e to the x and log x and what they look like before we worry about their tangent slopes. Before I evaluate e to the x, y equals e to the x, let's figure out what e is. So what is e? Is it like a variable? Is it a constant? Is it a theory? What is it? Mr. Meyer, what do you got? 2.71. Yeah, so it's a constant like pi. It's called the natural constant. Okay? It's a number. So pi is a number. Do you know how to calculate pi? Besides just plugging into your calculator and see that's 3.1415926.535. Circumference over the diameter. For any circle, if you look at the circumference of the circle and you take the diameter, so here's the diameter. If I take this diameter and I lay it on top of the circle, I'll be able to lay it on top of the circle 3.141592653 times, which is cool, okay? And it's visually cool to kind of think about that, and there's been some videos where you see it kind of curve around. But that's it, 3.14 times to get that around. Well, E is this. The limit as x approaches infinity of the following. 1 plus 1 over x to the x. And that's about 2.718. So in your home screen in your calculator, you can check to see that's true. I can plug in E, that's over the division symbol. Press enter, you can see what that constant's equal to. But you could also try and go 1 plus 1 over some big number, like 1, 2, 3, 4, 5, 6, 7, 8, 9, and take that to the 1, 2, 3, 4, 5, 6, 7, 8, 9th power, and you'll notice you get pretty much the same number. And if you plugged in bigger and bigger numbers, you would get a more and more accurate number. E was kind of developed looking at compounding interest continuously. It is applied in various fields of mathematics. Okay? But typically, E is looked at in this form, e to a power x, y equals e to the x. And we could graph y equals e to the x using our calculator, and we see that it looks like this. It's kind of approaching 0 as we're going to the left, and then it grows exponentially as we grow to the right. Okay, the most obvious point of e to the x is 0, 1. Anything to the 0 power is 1. So that's good. Well, when we talk about e, we have to talk about its sister, its inverse log, the natural log of x. So e to the x and natural log x are inverses of each other. Inverses being like they undo what the other one does. You guys have dealt with inverses. We're going to look at inverses even more next class. But say on like the last test, if you tried to figure out what theta was and you had tangent of theta is equal to 1, the only way you can undo what tangent is doing to theta is by taking the inverse of both sides. And that undoes what tangent does, giving you theta is equal to tan inverse of 1. Well, if I have, I don't know, 5 equals e to the x, or e to the x equals 5, let's do that instead. And I want to solve for x, I got to undo what e is doing to x. To undo it, I would use the inverse function. Now we're not going to do e to the negative first power, but instead we will use log, and we'll take the log of both sides, the natural log. Natural log of e undoes each other, leaving us with x is equal to log of 5. What's great is that in my calculator I can type in the log of 5, and I can take e to that power, and I figure out that e to that power is 5. Okay? So what happens when we're looking at the graph of log of x is whatever e does to x, log will undo it, bring it back to where it originally started. So this is why inverses, when you graph them, are reflected over the y equals x axis. So there's e to the x, there's log x reflected over the y equals x axis. You could do that for any. If you looked at the graph of tangent and then the graph of your inverse tangent, you would see it's just that same reflection. So this is log x. Now it's cool. Now log is not a number. Log is a function. A function like, you know, some trig function like sine. So you can't just type in log and get a number. It doesn't make sense. You can't just type in sine and get a value. It's the log of something. It's the sine of something. It just talks about the relationship of you know, either right triangles or of these exponentials. So this I can plug into my calculator, great, but there's some specific points on the graph of y equals log x that we need to kind of be able to develop ourselves. Specific values are like log of 1 or log of e. You need to know these values, kind of either memorized by heart, or you need to produce the answers for them. Now the way I do this is I kind of go the other way around. Knowing that log and e are opposites of each other, what I do is I take the log of 1 and I set it equal to some y value. Then, to undo what log is doing, I'll take e to the power of both sides. Kind of just like what we did the other way around by taking the log of both sides. If I want to get rid of log, I take e to the power. This gives me 1 equals e to the y. Well, this should help me discover what y has to be. E to what power equals 1? 0. E to the 0 equals 1, so the log of 1 equals 0. You guys try to figure out what log of e is equal to without using your calculator. If I take e to the power of both sides, I get e equals e to the whatever variable I choose to use. So let's use like y or x or whatever, e to the power. I get e is equal to e to the y. Well, what does y have to be? 1. Log of e is 1. This can be confirmed in your calculator. Log of 1 is 0. Log of e is 1. Okay. Now, similarly, if we do this with e cubed, we'd see the log of e, which is just kind of 1. They undo each other, just leaving us with 3. And if I look at something like log of 4, I'm not going to be able to know the exact answer, but I should be able to approximate the answer using the same kind of procedure. So it's a number. Let's figure out what the number is going to be. I take e to the power of both sides. I see 4 is equal to e to some number. And now I got to think, well, if I take e to the first power, that's 2.7. So that's less than 4. But at the second power, 2.7 squared, well, I know 2 squared is 4. So 2.7 squared has got to be bigger than 4. So I know this number has to be between 1 and 2. It's probably going to be closer to 1 than it is to 2. That's all I need to do. And to confirm that, I can take the log of 4 and show that it's actually 1.38. But on a AP question, you might have to be able to figure out that that value is going to be between 1 and 2. Maybe you're seeing if this function is increasing or decreasing, or you're doing one of those sign charts. You're going to have to be able to compare values without using your calculator. So we need to be prepared for that. So those can be plotted. So if this has 0, 1, this has 1, 0. Another one would be if I plug in 1, we'd get e, because that's e to the first power. But here I'd have to plug in e to get 1. Okay, inverses, they flip-flop each other. Whatever e does to an x, log will bring it back to where it starts. If 1 goes to e, e will come back to 1. Kind of a mapping situation. Let's talk about the limits really quick. You can just look at the graph, or you can remember back what we did in Unit 2. So the limits of e and log and a. As x gets bigger, e to this power will continue to grow. This will be equal to infinity. That's something we should just kind of understand and know. A very common mistake made is on this question. Everybody thinks since this limit is positive infinity, this limit must be negative infinity. But that's not right. That's what you would think, right? Instead, if you think about plugging in a negative value that's huge in for x, you know that this is in an exponent. And we know if we have a negative exponent, it can be written as 1 over that thing to the positive exponent. And we should remember if we have a constant divided by something infinitely large, we get something infinitely small, which is essentially 0. Okay, so it's not positive infinity and negative infinity, it's positive infinity and 0. So highlight this, circle this. This is an important thing to remember and to understand the concept of. Now let's look at the limits for log. If I look at the graph of the log of x, you can see, it is increasing, but it looks like it might trail off and just hit like a horizontal asymptote, right? It looks like that. But that's actually not the case. It will continuously grow, but unlike e to the x, which grows exponentially quickly, log x will grow exponentially slowly, but it will grow. It'll never kind of peak at a certain value. And you can think of that by using different values or different powers of e. E to the 100, huge number, gigantic number, e times itself 100 times. Well, the log of e to the 100 is 100. Okay, so if I'm talking about this as my x value, this would be my y value. Well, if I plug in a bigger value or a bigger power, like e to the 10,000, that much bigger than e to the 100, a gigantic number, well, it would produce an increasing y value. The difference between these two values far, far greater than the difference between these two values, but this just displays how we are growing instead of just peaking and stopping our growth. We will continuously be able to produce bigger and bigger y values. We'll just have to plug in bigger and bigger x values. Okay, now the second question, the limit as x approaches negative infinity of log x. This actually does not exist. If you look at log, log starts right here to the right of 0. You actually cannot find a value of log of 0 or of log of any negative number. And if you think about it, why that's the case, if I do that whole switcheroo, I get 0 is equal to e to the y. There's no value that I can plug in for y to make e or any number to a power equal to 0. E to the x is always positive, so that means we can only have positive values that we take the log of. Same here, there's no value that I can plug in for y to make e to the y -1. I mean, you could try with your calculator if you want to, just to see. If I plug in e to the, like, -1,000, I'm not going to get a negative number. I get essentially 0, but it's not 0. It's close to 0. E to the -5. I'll get a very small decimal. Okay? So you'll never have e's that will produce 0 or negatives. E to the x is always positive. And since e to the x is always positive, you can only plug in positive values for x. X has to be greater than 0. Okay, let's do one more limit problem. Let's do this one in the middle. So it's the limit as x approaches infinity of 3x times 2 to the -x. Just to remember one extra concept from back in Unit 2. So if I wanted to, I could rewrite this as 3x over 2 to the positive x, right? And then I plug in, or I think about plugging in bigger and bigger values. What does this limit equal? If I plug in infinity, I can think of it being infinity over infinity. Does that really help me? Is that like 1? Is that 3/2? Mr. Beard, what are you saying?
The denominator has the 1 at the power.
Yep.
The numerator becomes insignificant because the denominator is so much greater, so it becomes 0.
That's exactly right. This limit is actually 0. And we got to remember it's all about what's going on as we're plugging in bigger and bigger values. Since we have this x in the exponent, any exponent, any number to any exponent will grow significantly faster than a variable to any power. So yes, this will grow, but this will grow faster. So if you have something that's growing faster over something that's growing slower, well, this will be a bigger number compared to a smaller number. This will be a fraction, something less than 1. And as we continue to grow faster and faster, the numerator will become less and less significant, making it just like a constant divided by a huge number, which will be essentially 0. Okay, so remember stuff like that from back in Unit 2. All right, cool. Well, that's just kind of like an intro, I think. Yep. Now, what we want to do is figure out the slopes of the tangents of log x and e to the x. Right? We're in calculus. We deal with slopes of tangents. So let's find the derivatives of e to the x and log x. Now, and to do this, we're going to do a little activity where we actually use our calculators to find these slopes of these tangents. And then hopefully after we use our calculators, we will be able to develop like the derivative rule for e to the x and for log x. And that'll kind of be almost all of our derivative rules that we need to know after we do these two. Okay? So we're going to start actually with the log. We're going to look at the slopes of the tangents to log first. And then we'll go back up to do e. Okay? So, how to find derivatives using your calculator. Two methods. Method number one is to use y equals. So in my calculator, if I want to, I can type into y equals the function that I want to take the derivative of. So we're going to do log x at 1, 2, 3, and 4. Now, our calculator is great at computations. It's great at producing decimals and to do, calculations with lots of decimals and, points that are close together or far apart, whatever. It's good at that. What your calculator can't do is tell you what the derivative of log x is. If I ask my calculator what the derivative of x squared was, my calculator, unless you have an 89, is not going to tell you it's 2x. It can't do that unless you have an 89. Instead, what it needs is it needs a point. It needs to say, okay, I can't do this to give you a function, but if you tell me a point that I need to look around, I could do a pretty good job approximating that the slope of x squared at 1 is 2. It's not going to go from x squared, use the product rule, not the product rule, the power rule to tell you that the derivative is 2x and then it's plugging in 1 in for x like you guys do. Instead, it does calculator things. What do you think the calculator does to estimate that this derivative is 2? It's the way you guys first estimated a tangent slope. Yeah, test points. 2 points, what? Where was our test points located, Adam?
Be like, I can't remember, but it was like close, really close to where the answer is, so like it gets like wider and then it gets smaller.
Exactly. Your calculator takes 2 points really, really close to the actual point that we're trying to find the tangent, and it goes so close that it can pretty much say what the tangent slope is going to be equal to. But it's still an approximation. Okay? So to show what the calculator does, let's look at log x. It won't tell you what the derivative function is. It won't tell you what your slope generator is. But if you go into second calc and you click on dy dx and you give it an x value, it will tell you, so let's do that. In y equals, I go to second calc. In calculate, I see dy dx. So I can press 6 or select it. And then I say, okay, I want to find the slope of the tangent at 1. I plug it in, and it tells me it's 1.000003. Now, it gave you that big decimal because they're giving you an approximation. You could probably assume that the exact value of the tangent slope is 1, and you'd be correct. However, your calculator is not good with exacts. It's good with approximations. So your calculator just told you that the derivative of log x, when x is 1, was 1. Okay, interesting. Well, let me show you the second way to find derivatives, and we'll do the derivative of log x when x is 2. So I can go into my home screen. So the second way is through the home screen. if you go to math and derive, math down to 8 is and derive. Everybody go there and click on it. Now, there's two things that could show up. This that you see here, all the way down to 8. Or you could see and derive. Who sees and derive in their calculator? Raise your hand. Okay, we'll get to you guys next. If you see this, this is what you would do. You'd go dx, make sure you type in x, then you type in your function that you want to take the derivative of, and then plug in the number. Okay, so that's for the people who see what I see right now. So x, the function log x, at the specific number 2. We can essentially say it's 0.5. Well, if you don't have this show up on your calculator, let me show you what you do see and what you have to do. Okay. If n derive pops up like that, you need to type in your function. So don't f of x. Type in log x, whatever your function is. So I go log x. Then you need to tell your calculator which variable you're using with respect to a specific variable. So you need to press comma x. So let's take the derivative of log x with respect to x, and then you have to press comma one more time and tell it the value that you want to take the derivative at, or the approximation. So if I want to check at 2 again, I do n derive log x with respect to x at x equals 2 to get that value. Okay, did everybody with the old calculator figure that out? If you don't type it in exactly like this, you'll get an error, you'll get frustrated. Yeah, using whichever method that you choose to use. Now, if you have, I think either calculator, you can always press second entry, and you can just change the number to do 3 and 4. Or you can always just go into your y equals and go, dy dx and plug in the different values. But you guys right now figure out what the derivative of log x at 3 and 4 is. I just did 1 and 2. And if anybody needs help or their calculator isn't working, let me know. I will see if I can figure it out. Do you have the 89?
Yeah, okay.
So the 89.
I know how to do it. It's just actually go to home.
Yeah.
And then you go to 3, and then you everything from there.
Right. And you just have to type in
Function of
the x. Yeah.
Already.
I know. I want to make sure I can do it.
Okay. No, I was talking about. I already knew it.
Yeah. 89's actually, they can give you the derivative. I'm not actually sure how they does it, but do you know how they do it?
No, I don't.
No, I don't know either. It's almost like they just have the rules programmed in there.
Exactly.
Yeah. All right, Miss Emma, did you get it for 3? What'd you get for 3? Cool. Mr. Magnello, what'd you get for 4? Okay. Well, let's rewrite that. So the derivative of log x at 1 is 1, at 2 is 1/2, at 3 is 1/3, at 4 is 1/4. Guess what the derivative at 5 is? 1/5. Okay. So in general, the derivative of log x, what do you think it is? 1/x is correct. Okay, that's your first new derivative rule that you're learning. The derivative of log x is 1 over x. Now we want to figure out what the derivative of e to the x is. You guys try to figure it out by finding the derivatives of e at 0, 1, 2, 3, and 4. What's up?
I don't know how to use this all.
We just went over it.
I know what I'm doing.
You have to do n derive of your function. Okay, so n derive of your function. Okay, comma. You have to put a comma. You have to tell it with respect to a specific variable. So you do log x comma x, and then you have to tell it at an exact point by doing comma 2. Okay, so do that right now. All right, so we're doing e to the x. We're doing it at 0, 1, 2, 3, and 4. Just, round your decimals to 3 decimal places. Not as obvious as log x, right? But turns out this is the easiest derivative rule out there. Can anybody who doesn't know it already figure out how you produce those tangent slopes in general? You already know it, Mr. Magna, because you're in physics?
No, it wasn't.
You just know it?
Well,
Okay, so did you figure it out? Yeah, it's e to the x. Turns out the y values of e to the x are also the tangent slopes. There are no other functions that this occurs where the values of e to the x give you also the slopes of the tangents. Kind of have to think about that for a little bit. If I graph e to the x, the values that I see on e to the x are also the slopes of the tangents to e to the x at those points. So if I trace over to this point at 0.851 with that y value of 2.34, at that specific point, the tangent slope to that graph is also 2.34. Crazy. E to the x works in magical ways. So the derivative of e to the x is just e to the x. You want to find the slope of the tangent? Look at the point that you're on. Okay, now, derivative of a to the x. Turns out the derivative of a to the x is similar to e to the x. Derivative is a to the x log a. Now, I'd want you to confirm that using your calculator with 3 to the x at, say, 2. So why don't you confirm that the derivative of 3 to the x at x equals 2 is equal to three squared log 3 by finding the derivative using your calculator. Sweet. Now, which way do we prefer, the y equals method or the home screen method? Home screen? It's really weird. Some people like, yeah, some classes are like, oh, y equals, totally. Some classes, home screen. I would say that if you have the older operating system, you'd probably like the y equals because the n derive with all the stuff, sometimes gets messy. But whatever floats your boat. So x equals 2. 9.8875. And that's also, if we confirmed, using our new derivative rule that we learned, equal to 3 squared log 3. 3 squared log. Okay, now, probably wondering the difference between the ln and the log. Does anybody know the difference?
The log of b.
Yeah. ln stands for a log base e. So ln is the same as log base e. If you want to solve for x in a situation like this, you would need log base e, or ln. If you have any other number, though, like 7, the only way you undo what 7 is doing to x is to use logarithms, but with a specific base, log base 7. And I would do log base 7 of both sides, and I'd get x is equal to log base 7 of 5. And we'll go into how you can find that, but the log button that's just log stands for log base 10. Okay, so if I have e to the x is equal to 5, I use natural log on both sides. But if I had something like 10 to the x is equal to 32, I would use the log button on both sides to get that x is equal to log of 32. So the bases help account for the different bases with the different powers. So we will be using just e to the x's, and therefore we'll just stick with natural log. So don't use the log button unless you see 10 to the x, which you won't see. Okay, cool. Now, let's talk about if we have a chain rule situation with e and log and a. So let's now focus more on the derivative rules we just learned, which were the derivatives of e, log, and a. If I have e to a function, or log of a function, or a to the function, I'd have to take the derivative of this using the chain rule. Now the key to the chain rule is to identify the outside and the inside. Well, the outside for e to the f of x would be the e to the power. And the inside would be considered whatever is the power. Well, if I want to take the derivative of e to the f of x, I would take the derivative of the outside, leave the inside alone, times the derivative of the inside. So that'd be e to the f of x times f prime of x. Simple. The derivative of e is just e. But it's not the derivative of just e. The derivative of just e is 0, but the derivative of e to a power is e to that power. If I have log of f of x, I'll have an outside and an inside. The outside will be the log of the stuff. The inside will be the stuff. If I want to take the derivative of it, I take the derivative of the log. The derivative of the log of stuff is just 1 over that stuff times the derivative of that stuff. So, derivative of the log of a function is 1 over the function times the derivative of the function. And a is similar to e. It would be a to the f of x, just with an included of a log base e of a times f prime of x. Okay, but I don't want you to have to memorize these rules. I just want you to understand that it's still the chain rule. The chain rule still applies. So if I tell you to take the derivatives of these two guys, you should be thinking chain rule. So take the derivative of e to the x squared and take the derivative of log of 4x cubed minus x. Just the derivative of the outside, leave the inside, times the derivative of the inside. What'd you get, Mr. Wenzel, for the first one? Piece of cake. Chain rule. Derivative of the outside times the derivative of the inside. Do the second one. Derivative of log is not log. Good. Derivative of log of stuff is just 1 over that stuff. 1 over x is the derivative of log times the derivative of that stuff. Just make sure it's in parentheses. If you wish, you can move it to the numerator, but you don't have to. Okay, a couple more. Let's do e to the negative x. This is a very common one. You'll have to take the derivative of e to the negative x. A lot of people make mistakes on it because they think the derivative is just e to the negative x, but you know that's not true, Ms. McMaster. What'd you get, Ms. Bonke, for e to the negative x? Perfect. E to the negative x times negative 1. or negative e to the negative x. This guy would just be 3 e to the negative x plus e to the x squared times, this would be e to the negative x times negative 1, so that's negative e to the negative x, and the derivative of e to the x is e to the x, and that'd be it. Down here, derivative of 5 to the x would be 5 to the x log 5. So 5 to this function would be 5 to this function log 5 times the derivative of this function. You guys try 2 e to the negative x. All that. And we already did a couple logs. So this one, it's kind of like a trick. The derivative is just 1 because you get 1 over e to the x times e to the x. The reason why that's a trick is because log of e to the x is just x, and derivative of x is just 1. You can do the same thing with e to the log x. You have e to the log x times 1 over x. That should just give you x. Let me think about that. E to the log x, derivative would be e to the log x times 1 over x. That's just 1 as well. Okay, we'll skip this one. This is just a little mess. Well then, I could give you this question. Looks complicated, right? But it's not. You'll see questions like this on the AP exam. So there's going to be a question like this on your quiz and on your test because you have to be used to it. Does this look familiar at all?
Yeah.
Looks familiar. From when did we see this? It was Unit 2, and what was it that this was familiar to? And we got 0 over 0 a lot when we tried this and we plugged it in. But that's not it. This should look like the definition of a derivative. you remember when we first introduced derivatives, we said, okay, it's just 2 points infinitely close together using the slope formula and using any 2 points on any function. We developed that. That was the definition of derivative. The first thing you did to figure out answers like this is you used algebra. And there were some students who already knew derivative rules who were like, well, do I really have to do this method if I already know the rules? And I said, yes, but just for a little bit, because then we're going to learn the rules and you don't have to worry about this again. Well, now you kind of have to worry about this, but not in the same way as you did before. We're not going to use algebra to figure this out. And the answer is not 0 over 0. Okay? Instead, what we need to do is we need to connect this stuff with what this means. This is just the derivative of my function. And you can find the derivative of a function by using the definition of a derivative, or you can use derivative rules. Now, instead of x plus h, if I replace this x with a 5 or something, this is not just the derivative of my function, but it's the derivative of my function at a specific value. So what we need to be able to do is see this and say, oh, this is just the derivative of the log function when x is 5. That's all that is asking, that limit question. You need to be able to tie the two together. So what's the answer? 1 over 5 is correct. The derivative of log is 1 over x. Plug in 5, you get 1 over 5. If you tried to figure this out algebraically, maybe you could. I don't know. Wouldn't know what you would do to even start that. Maybe you could figure out that it's 1 over 5. Okay, tricky, right? This is what the AP exam does to us. Force us to combine rules and definitions with questions. Let's look at this guy. Limit as x approaches 3 of e to the x minus e cubed over x minus 3. This brings us to the alternate definition of a derivative. This is the same as the derivative of your function at a specific point C. So this is usually used for derivatives in general. This is used for derivatives at points. So what you need to be able to do is connect this to this to realize this is the same as the derivative of e to the x when x is 3. Derivative of e to the x is e to the x. When x is 3, the answer is e cubed. Okay, your turn. This guy first. Limit as h approaches 0 of the cosine of pi over 2 plus h minus the cosine of pi over 2 all over h. Doesn't have to deal with logs or e's, but it's the type of question that you will see. Because I don't want to try to figure this out algebraically. I'm sure you can. ACC, huh? Is that ACC? College is not like that, guys, okay? I hope you know that. All right. Okay. Who got an answer? Strobel tree, did you get something? Yep, what's that equal to?
So you take the derivative of that when the negative sign times that times 0 is 0?
No. Good question, though. A lot of times people make mistakes and they think this is the derivative of cosine of pi over 2, right? Well, cosine of pi over 2 is 0. The derivative of 0 is 0. That's actually not the case. This is actually asking what the cosine of x is when x is pi over 2. The derivative of cosine is negative sine. Then you plug in pi over 2, you get negative sine of pi over 2. Sine of pi over 2 is 1. The answer is just negative 1. Tricky, right? Now, the last one is even a little bit trickier. We know this is the derivative of something at what point? What do you think, Miss Pennington? No clue? In this situation where you have a number and it's not 0, that's your number. If you have a 0, you're looking for what's inside your function. Okay? Now, this is the alternate form of the definition of a derivative. That's f of x minus f of c all over x minus c. So if you just look at this first part, this is your function. Okay? And in the first one, this is f of x plus h minus f of x all over h. This would be the function. This would be your x. Okay, so this would be 1 over x plus 3, which is 1 over 8. Okay. Moving on. Those are tricky problems, but we have to at least talk about them once. You'll see them on your midterm. You'll see them on your test. All of the above. Let's do some application problems involving log and e. We won't get to all these, but I'll have them all in the video. This will be the largest lesson of this unit, so most of the problems on your test will be a little bit more problems from this lesson than from the other lessons that you're going to learn. All right, Ms. Gross, how do I find locations of horizontal tangents to functions? Exactly, the numerator of what? Exactly. The derivative equal to 0. If the derivative is a fraction, we set the numerator equal to 0. Let's see if we have a fraction here. And if we don't have a fraction, then it's just the derivative equal to 0. So let's find the derivative. Everybody find the derivative of x squared minus 3 e to the x. Understanding that we have a product, and we must use the product rule. F prime g plus g prime f. Derivative of the first times the second plus the derivative of the second times the first. Okay. I want to set that equal to 0. And I want to solve this. Not really fun, right? As it looks right now. But it's actually not that bad. The key is that. Yeah, e to the x in both terms, you can factor it out. A lot of times when you're dealing with questions like this, you'll always factor out e to the x. Okay. And then I'm going to see if I can figure out what this stuff is in the middle by factoring. And I get x plus 3, x minus 1. So that gives me an answer of negative 3 from this guy. Gives me an answer of 1 from this guy. But what would be the answer from e to the x? When is e to the x 0? Negative infinity, but that's not a number. It's a concept. So never. E to the x is always positive. So there are no solutions that come from us factoring out e to the x. It's just at negative 3 and 1. Those are the x locations. Now, if we're trying to find x, y, it might be messy, but you'll still get a value. You plug in negative 3 here, you get 9 minus 3 is 6 times e to the negative third. That's a y coordinate. Don't be afraid to leave it like that. I use the x coordinate of 1, plug it back in, I get negative 2e. That's a y coordinate. Don't be afraid of that either. Okay. Next problem. It'll be the last problem we can get to, but there will be more on the video. It's a good problem. Yes, that's e to the kx, where k is a constant. What value k does f have a critical point at x equals a half? Critical points. Are they my first derivative or my second derivative equal to 0? First. It's not just 0, it's or undefined. We don't have to worry about undefined in this case, but maybe other situations we will. Okay. So I'm told that this derivative, which using the product rule gives me the following. F prime g plus, what is the derivative of e to the kx? Close. It's k e to the what? Not just x. Kx. The derivative of e to the kx would be the derivative of e, which is e, leave the stuff alone, times the derivative of kx, which would just be k, because k is just a number. So that's the tricky part that we need to be comfortable doing. Times x squared. Okay. We are told this equals 0 when x is a half. I can just plug in a half right now and figure out what k is. Maybe I do that. Maybe I want to simplify this first before I plug in a half. Let's plug in a half. Let's just go for it. If I plug in a half, I get 1 e to the k times 1/2 plus e to the k times 1/2 k times 1/4. Well, I need to figure out what k has to be so that this is equal to 0. Maybe you can see it now, or maybe you need to factor out this e to the k times 1/2 so that you just have 1 plus k times 1/4. Maybe now it's easier to see what k has to be. This will always be positive. K will have to be -4 for this to be true. You'll see questions like that on your quiz and on your test. And there are more questions that I will do that deal with finding concavity, functions increasing, decreasing, etc. I'm going to do on that. And we have implicit differentiation, which will be on the video. All right, next problem. Find when f of x, which is equal to x squared e to the x, is decreasing. Well, how do I know when a function is decreasing? That's when the derivative is negative. To figure out when the derivative is negative, I need to find when the derivative is 0. And then I will analyze the signs of my derivative around those zeros. So let's start by finding the derivative. I get 2x e to the x plus e to the x, x squared. I'll then factor out an e to the x. That's the common step in these problems. I can also factor out an x. That gives me solutions. This is always positive. However, this is 0, and that'll make the entire thing 0, and this is -2. So since I factored out this x, this can give me a solution of 0. So now on my number line, I will evaluate the signs of f prime, and as long as I found all of the correct zeros, this is going to work out. Now, since e to the x is always positive, if I plug in a value like 5, this is positive, this is positive, this is going to be positive. If I plug in a negative value, this is still positive. This is now negative. This is still positive. So positive, negative, positive is a negative. And then I plug in a value like -4, positive, negative, negative, positive, negative, negative, positive. So when are we decreasing? Between -2 and 0. F is decreasing. And because f prime is less than 0 on that interval. All right. Find the concavity of f of x, which is equal to x log x when x is 6. Okay, so concavity, concave up or down, we need to analyze f double prime at x equals 6. And if it's positive, we're concave up. If we're negative, we're concave down. So let's do it. First derivative, we have a product, so be careful. It's a sneaky product with just having an x, but we can see it is. So we have f prime g plus g prime f. Now f prime of x is equal to log x plus 1. I can now take the derivative of that to get the second derivative. That's 1 over x. This is telling me that so long as I'm plugging in x's that are greater than 0, which I have to be, we are going to be concave up everywhere. Okay. Let's just confirm that. X log x, I hope, is concave up everywhere. Yep, looks to be concave up everywhere, which is great. Next problem. If f prime equals 1 minus log x, when would f of x be decreasing? So I'm given my derivative and asked when the function is decreasing. Okay, well, when we're decreasing is when our derivative is negative. To figure out when my derivative is negative, I need to first find when my derivative is 0, and then analyze the signs around that to see when it's negative. So let's figure out when 1 minus log x is equal to 0. Now if I solve, I get log x is equal to 1. Now I got to figure out what x is. This is one of those times where you would use your inverse to figure out that x has to be equal to e. So I use e to the power of both sides to free up x from the clutches of log, so that I just kind of cancel this stuff out and leave us with x. Over here I have e to the first power. So e would be the only time when that derivative is 0. Now I need to figure out the signs around e, and this is where, it gets a little tough. So let's think about our derivative, 1 minus log x. Well, if I plug in bigger and bigger values in for x, so bigger values in e, we know that log is increasing. If I think about like e to the 5th power, that's a bigger number than e. This would be 5. 1 minus 5 would be negative. So the way I did that, I did a bigger number like e to the 5th. I know that the log of e to the 5th is just 5, so I know that's negative. Okay. Now I think about a number less than e. Now this is where it's tricky, but like a number less than e would be like 1. That's easy to work with. And we got to remember that the log of 1 is 0. Why? I take e to the power of both sides. I get 1 is equal to e dx. X has to be 0 for this to be 1. So I get 1 minus 0. Well, that's a positive. Must be positive over there. So since x has to be bigger than 0, maybe we'll just start at 0 to e, and then e on. When is f decreasing from for all x's bigger than e? That would be it. Since f prime is negative, or since f prime is less than 0 on that interval. Now, we might have certain questions, and you have them on your homework, where you're asked to implicitly differentiate things with logs or with e's. So let's start with one with log. Now, we can't forget about implicit differentiation. I would take the derivative with respect to x of both sides. Now, I have stuff with x's and y's in here. So the derivative would be 1 over this times the derivative of x squared minus y. Derivative on the right side is just 3. Now, remember, if we have these parentheses going on, we can either distribute this, or if we could get rid of it somehow else without, messing things up, we could do that. I'm going to multiply both sides by x squared minus y. I have 2x minus dy dx equals 3 times x squared minus y. Then maybe I can add dy dx, subtract that to get dy dx is equal to 2x minus 3x squared minus y. Okay, that's your second derivative. You did it. Let's see if it gets more complicated with this. Probably will. Let me shrink this. So let's take the derivative with respect to x. I get 1 over x plus y times the derivative of x plus y, which would be 1 plus dy dx, equals, on the right side, I would get f prime g plus g prime f. Now, dy dx is on both sides. If I tried to multiply by x plus y like I did in the last problem, that would create a problem over here because I'd have a dy dx that was trapped. The only way I would do this is by distributing that 1 over x plus y. I got 1 over x plus y plus 1 over x plus y times dy dx equals y plus dy dx x. Now we are ready to move stuff around. I'll subtract that. I'll factor out a dy dx on the right side. So I have 1 over 1 plus y plus a negative x, so that's going to be a minus x. Equals y minus 1 over x plus y. I then can divide to get dy dx. Hope everything is going well. My computer seems to be slowing down. And you got that. And that's good. And we could do the same thing with like a implicit equation with e. You know, maybe we have x plus y in the exponent of e. When I took the derivative, it'd be e to the x plus y times the derivative, which would be 1 plus dy dx. And over here, I have 1 plus dy dx. Now, see these parentheses, the only way to really get rid of these, because I have dy dx's on both sides, is to distribute. When I do that, I get e to the x plus y plus e to the x plus y dy dx, which is equal to 1 plus dy dx. And then I can solve for dy dx. I'll just do this all in one step. I'd get 1 minus e to the x plus y over e to the x plus y minus 1. Okay, so that would be it. Hopefully this video is working, and that's all you got. Good luck on your homework.